April 15, 1944, England, Lieutenant Commander Harold Parker stands at the edge of a British naval dock staring at what appears to be a pile of welded steel boxes. Each one measures exactly 5 high by 7 long by 5 wide, simple, industrial. Unremarkable, just sheet steel bent and welded into rectangular containers. Stacked like children's blocks waiting to be assembled into something greater, Parker runs his hand across the cold metal surface, no complexity, no sophisticated engineering, just a hollow steel box with bolt holes drilled at precise intervals along reinforced edges. This cannot be the solution, he thinks. This cannot be what will land an armored division on a hostile shore. But it is. In 2 months, these unassuming steel cubes, Captain John Lake's naval pontoons, will solve the most critical logistics problem of the largest amphibious invasion in human history, when landing ship tanks ground to a halt 300 feet from the Normandy beaches, unable to reach dry sand, when thousands of tons of armor and vehicles sit stranded in the English Channel with German artillery zeroed on their positions. These simple boxes will be the difference between catastrophic failure and ultimate victory. The concept seems almost absurd in its simplicity. Connect 180 of these pontoons together, 30 long by 6 wide. Add 2 143 horsepower outboard motors. The result, a self-propelled floating platform 150 long and 42 feet wide, capable of carrying 275 tons of cargo at 4 knots through shallow water where no purpose-built landing craft can operate. The Americans call them rhino ferries. The British, initially skeptical, now call them essential. Parker watches as CBS from the 81st Naval Construction Battalion bolt the pontoons together using the ingenious fastening system designed steel stringers held by iron wedge pins that create a rigid structure without excessive strain on individual connections. 3 days earlier, he'd observed these same men assemble a complete rhino in under 8 hours. Tonight, under cover of darkness, another 6 ferries will take shape on this dock. The invasion clock is counting down. Operation Overlord demands solutions that work, not solutions that look impressive. And these boxes, Parker realizes, represent military engineering stripped to its absolute essence. Function without ornament, capability without complexity, effectiveness without elegance. The question that haunts every planner from Eisenhower down to the beach battalion commanders is stark. How do you land an army on a fortified coast when the landing craft can't reach the beach? But there it was, the ingenious proof that would change everything. If you want to see how this simple solution rewrote the course of the largest invasion in history, support us with a like. It helps us uncover more buried stories like this. Subscribe if you haven't already. The answer floated in Falmouth Harbor disguised as industrial scrap metal. The journey to this moment, Parker knows, began 4 years earlier in a Washington office with a civil engineer, a pile of cigar boxes and kite sticks. The journey to harbor had begun in March 1939, when Commander John N. Locke reported to the Bureau of Yards and Docks in Washington, D.C., born in Massachusetts on May 18, 1892, had graduated from the Naval Academy. 1914. By 1939, plagued by severe headaches and partial deafness, Admiral Ben Morrell transferred him to the less position of War Plans Officer. It was meant to be compassionate reassignment. Instead, it became the assignment that would help win the war. Inherited a file full of materials relating to advanced base facilities and amphibious equipment. The problem was clear: in any Pacific war against Japan, the Navy would need to establish bases on undeveloped islands with no ports, no piers, no infrastructure whatsoever. Existing solutions, pneumatic pontoons, were cumbersome, unreliable, and prone to failure. Needed something universal, something that could be mass, easily transported, and assembled by sailors under fire into whatever structure the situation demanded: causeways, barges, dry docks, piers, floating cranes, anything. Around July 1940, began collecting empty cigar boxes from every concessionaire in the Navy headquarters building along the National Mall. Back in his office, he arranged the boxes in rows, spacing them evenly. Then he connected them using wooden strips from children's kites, fastening the strips to the corners with small nuts and screws. The result was a rigid floating beam. Multiple beams could combine into a platform of any size. The model demonstrated that individually small, uniformly sized pontoons could be connected into structures strong enough to support massive loads. The critical breakthrough came in August 1940 during Lake Hawk's family vacation. He solved the fastening Problem: how to connect steel pontoons in a way that provided strength, durability, and ease of assembly under combat conditions. His solution: steel stringers running across joints held by diagonal wedge pins that distributed stress without concentrating it at any single point, through trial and error. Applying military requirements for weight, buoyancy, and capacity, designed the standard pontoon 5 t high by 7 long by 5 wide, hollow welded steel construction. Pre-drilled bolt holes, curved bow sections for watercraft, simple enough for semi-skilled workers to assemble. Rugged enough to survive combat conditions. On February 18, 1941, contracts were awarded to the Pittsburgh Steel Corporation for 3 experimental assemblies, a 50-foot barge, 100-ton dry dock, and a seaplane ramp. Following successful tests, the Navy ordered 3,000 pontoon units. Training for pontoon crews commenced at Harbor, adjacent to the Advanced Base Depot in Island, under Lieutenant Commander Harold T., who would later command the Bobcats, the first CB unit to deploy overseas. Locke was promoted to captain in January 1942, just weeks after Pearl Harbor transformed his Pacific planning into immediate operational necessity. The pontoon's first combat test came in February 1942 when CBS took them to Bora Bora in the Society Islands. The construction battalions were pleased with the versatile magic box that could be assembled into whatever structure the tactical situation required, but the revolutionary application came from an unexpected source: a Royal Navy Reserve officer named Captain Thomas A., assigned to Combined Operations Headquarters. By late 1942, planning for the Allied invasion of Sicily was revealing a critical problem. Beach surveys indicated gentle slopes. Landing craft, especially LSDs carrying tanks, would run aground several hundred feet from dry land. The depth raid in August 1942 had demonstrated that seizing fortified port was catastrophically costly. The Allies needed to build their own port facilities on hostile shores. Aware of pontoons, inquired whether the units could form a floating road, a causeway to bridge the gap between ship and shore, working together, and designed overlapping causeways that could stretch 350, enough to reach from LSD to beach. On July 10, 1943, Operation Husky launched before sunrise. More than 3,000 ships landed, over 150,000 ground troops on Sicily's southern shores. Near CBS connected causeway sections under fire, allowing vehicles to drive directly from grounded LSDs to the beach. The causeways worked. The pontoon causeway had proven itself in combat, but were already refining the design for an even more ambitious application: the cross-channel invasion of France. Within weeks of the Sicilian landings, Captain Lake and Captain began refining the causeway concept into something unprecedented: massive self-propelled lighter barges specifically designed for the Normandy invasion. The tactical problem was becoming clearer with each planning session for Operation Overlord. Normandy's beaches featured tidal ranges of up to 18. At low tide, LSDs would ground hundreds of feet from dry land. At high tide, they could beach closer but would be stranded for hours, sitting ducks for German artillery. The solution emerged from fundamental insight: the same pontoons that formed causeways could be assembled into large, shallow draft barges capable of effing tanks and vehicles from LSDs anchored deep water directly to the beach. By late 1943, the concept had evolved into what the Americans designated the Rhino Ferry. The specifications were elegantly simple: 180 standard pontoons connected in a grid, 30 pontoons long by 6 pontoons wide, creating a platform approximately 150 long and 42 wide. 2 massive outboard motors, 143 horsepower each, provided propulsion. Total displacement approximately 275 tons. Speed when loaded 4 knots. Draft shallower than any LSD. The Rhino could do what no purpose-built landing craft could: operate in water too shallow for LSDs, carry loads too heavy for small craft, and be assembled from components that could be shipped across the Atlantic in the cargo holds of the very LSDs they would serve. Training commenced in the United Kingdom in late 1943. The 81st Naval Construction Battalion began assembly at Falmouth. November, initiating crew exercises in December. British Royal Engineers collaborated in the efforts at sites including Southampton. Early training revealed challenges: the 143 horsepower outboard motors were woefully underpowered for a 275-ton barge. Maximum speed was 4 knots in calm seas, in the channels notoriously rough. Waters, the ferries were nearly unmanageable without tug assistance. Engine reliability problems plagued initial runs, yet what they lacked in speed and maneuverability, they compensated for in versatility and capacity. A single Rhino ferry could carry 5 Sherman tanks or dozens of trucks or hundreds of troops or tons of ammunition and supplies. The shallow draft meant rhinos could operate in surf conditions that would beach an LSD and in water depths that would ground an LCT. By early 1944, approximately 55 Rhino ferries had been assembled specifically for Operation Overlord. The allocation was strategic: 31 ferries for the American beaches, Utah and Omaha, 41 for the British and Canadian beaches. Gold, Juno, and Sword. The pattern that emerged from months of testing was clear: Rhino ferries would never win any prizes for elegance or speed. They were slow, cumbersome, difficult to maneuver, and vulnerable to weather, but they could do one thing nothing else could: bridge the gap between success and failure. On D-Day, June 6, 1944, 6:30 hours, Omaha Beach, Normandy. The first wave has already gone in, bodies float in the surf, wounded men crawl toward inadequate cover. German MG-42 machine guns sweep the beach from fortified positions on the bluffs. Artillery shells bracket landing craft as they approach the shore, and 300 from the beach, LSD-21 grinds to a halt on Sandbar. The massive landing ship tank, displacing over 4,000 tons fully loaded, draws 14 of water when beached, but the tide is wrong, the gradient is wrong. Every calculation suggested the LSDs could beach at this location, but the reality of Omaha Beach in the chaotic first hours of the invasion is that assumptions are worthless and plans are disintegrating under German fire. Inside, LSD-21 British Army tanks idle their crews, listening to the sounds of battle echoing through the steel hull. Outside, the beach is a killing ground. Original plan called for the LSD to beach, open its clamshell bow doors, drop its ramp and discharge vehicles directly onto sand. Instead, the ship sits stranded offshore, its cargo of armor desperately needed but unreachable. This scene is repeating across miles of Normandy shoreline. LSDs ground out too far, LCTs struggle in the surf. Purpose-built landing craft designed for exactly this mission are discovering that combat conditions never quite match planning assumptions. The Germans have had 4 years to fortify these beaches. They know the tide patterns, they've plotted artillery for every possible approach, and they're making the Allies pay for every yard of sand. Then at approximately 7:15, soldiers on the beach witness something unexpected. Strange flat-topped barges appear through the smoke and spray, approaching from the transport anchorage several miles offshore. They look cobbled together, makeshift, almost comical in their progress through the swells. Each one measures approximately 150 long and 42 wide, massive floating platforms that sit low in the water, their decks barely above the waves. These are the Rhino ferries, and they're about to deliver the armored punch that will turn the tide at Omaha Beach. The technical reality of the Rhino's advantage becomes immediately apparent. Where LSDs require 14 of water depth when beached, the Rhino draws only a few feet, even fully loaded. Where LSDs must beach to discharge their cargo, Rhinos can drive right up to the water line, their flat decks allowing vehicles to roll directly onto dry sand. Where LSDs become immobilized for hours waiting for the tide, Rhinos can load, deliver, and return for another trip within the same tidal cycle. Aboard Rhino ferry, RHF-21 Chief Petty Officer James stands at the improvised helm, essentially 2 outboard motor controls and a rudder mechanism guiding his charge toward the beach. His ferry carries 5 M4 Sherman tanks. Their 30 weights distributed across the pontoon grid. The platform flexes slightly as waves pass underneath the pontoon's buoyancy, responding to but the bolted connections hold firm. The 143 horsepower outboard motors scream at maximum RPM, pushing the 275-ton load at barely 3 knots. Against the chop, spray cascades over the bow, the tanks secured with chains shift slightly with each wave. The Rhino is not graceful, it's not fast, but it works. At 7:32, RHF-21's bow touches sand before the ferry has fully grounded. Tank crews start their engines. The lead Sherman's driver engages gears. 30 tons of American armor rolls off the pontoon deck onto Omaha Beach. 4 more tanks follow within 3 minutes. By 7:40, RHF-21 is backing away from the beach, empty, preparing to return to the transport anchorage for another load. This scene repeats throughout the morning. Rhino ferries that American and British planners worried might prove too fragile for combat operations demonstrate remarkable Resilience, German artillery fire targets them, several take direct hits, some pontoons rupture, some motors fail. But the modular nature of the design means that even damaged ferries often remain operational, lose a few pontoons. And the barge still floats, lose one motor and the second can provide emergency propulsion, the simplicity. That looked like a weakness proves to be a strength. By morning a pattern has emerged, LSDs unable to beach. Effectively are being unloaded by Rhino ferries operating as shuttles, tanks and trucks that would otherwise sit stranded. Offshore are being delivered directly to the beach. The system isn't perfect, ferries are slow, vulnerable, difficult to maneuver in the surf, but they're delivering the critical heavy equipment that the landing forces desperately need. Staff Sergeant William, 1st Infantry Division, crouches behind a disabled tank on Omaha Beach and watches Rhino HRF-24 approach through a hail of machine gun fire. They look like something a child built, he would recall years later, just boxes bolted together with a motor on the back, but they kept coming, and every time one hit the beach we got more tanks, more guns, more ammunition. They saved us that day. The engineering genius of Captain Lake's design reveals itself not in sophisticated technology, but in basic physics and modular construction. Each 55x7 pontoon provides flotation for approximately 1.5 tons of cargo. 180 pontoons provide flotation for 270 tons, with a safety margin for the structure's own weight. The steel stringers that connect the pontoons distribute stress across the entire assembly rather than concentrating it at single points. The wedge pin fastening system holds firm under load but can be disassembled if needed. More critically, the design accommodates damage. A conventional hull-type vessel with it takes on water and sinks. With several punctured pontoons simply loses some buoyancy. Remaining pontoons support the reduced displacement. This resilience under fire proves invaluable on D-Day when German artillery and small arms fire riddle approaching ferries but failed to stop most of them from delivering their cargo. By nightfall on June 6, approximately 156,000 Allied troops have landed on beaches. Within 48 hours, over 130,000 American soldiers and approximately 17,000 vehicles have come ashore. The Rhino ferries operating continuously in 12-hour shifts are responsible for a staggering percentage of this throughput. The tactical picture is far from perfect. Omaha Beach saw approximately 2,400 Americans killed, wounded, or missing from the roughly 34,000 who landed there. Utah Beach's casualties were lighter but still significant. The invasion could have been far worse without the Rhino ferries bridging the gap. Stranded LSDs in the beaches, the armored support that turned the tide of battle might never have arrived in time. In the first 10 days following D-Day, approximately 85% of all vehicular equipment landed on Utah and Omaha beaches was delivered by Rhino. This single statistic reveals the truth that military historians would later document: the massive harbors, those engineering marvels of prefabricated concrete and steel, wouldn't be operational until late June. In the critical first hours and days of the invasion, when success hung in the balance, it was the humble, almost-looking Rhino ferry that delivered victory, the philosophy that produced the naval pontoon and its offspring, the Rhino ferry, stood in stark contrast to conventional military equipment design. To understand why, one must return to Commander's office in the Bureau of Yards and Docks in 1939 and grasp the impossible problem he faced. War Plan Orange, the U.S. Navy's strategic plan for war with Japan, envisioned island-hopping campaigns across thousands of miles of Pacific Ocean. Every advanced base would need to be established on islands with no infrastructure, no ports, no piers, no cranes, no warehouses. Everything would have to be built from nothing under fire, using equipment that could be transported thousands of miles aboard ships with limited cargo space. Requirements seemed contradictory. The equipment must be strong enough to support heavy loads, light enough to transport economically, simple enough for semi-trained personnel to assemble under combat conditions, versatile enough to serve multiple functions, durable enough to survive rough handling, weather, and enemy action, cheap enough to mass-produce in quantities sufficient for a global war. This brilliant insight was recognizing that trying to design specialized equipment for each specific need would fail. What if instead you designed single universal building block that could be configured into whatever structure the situation demanded? Mathematics were brutally simple. A floating structure's load capacity depends on displacement, the weight of Water it displaces equals the weight it can support, a hollow steel box 5 t high by 7 feet long by 5 t wide displaces approximately 2.1 cub-m of water roughly 2,100 or 2.3 tons, subtracting the weight of the steel box itself. Approximately 300 left usable lift capacity of roughly 1.8 tons per pontoon. These calculations drove the design. Army specifications required bridges and causeways to support vehicles up to 60 tons, standard roadway. Width needed to be 12 to 14. The simplest causeway configuration would be 2 pontoons wide at 5 t width per pontoon. That provided a 10 roadway. Narrow but adequate, length could be whatever the situation required, just add more pontoons for the Rhino ferry. The calculation scaled up. A Sherman tank weighed approximately 30 tons. 5 tanks meant 150 tons of cargo. Add crew, fuel, ammunition, and the structures. Own weight and the requirement approached 275 tons total displacement, at 1.8 tons useful lift per pontoon. That required approximately 153 pontoons minimum. The actual design used 180 pontoons, 30 long by 6 wide, providing a substantial safety margin. But the critical design decision, the one that separated its work from conventional military engineering, was the choice to optimize for simplicity over performance. A purpose-built landing craft could be faster, more maneuverable, it would have a hull designed for properly sized engines, sophisticated steering mechanisms. It would look like a proper military vessel, and it would require skilled naval architects to design, specialized shipyards to build, train crew to operate. Pontoons required none of this. The design could be executed by any competent steel fabrication facility. The components could be massed by semi-skilled workers. Assembly required no specialized tools, just bolts, wrenches, and basic mechanical understanding. Operation required no sophisticated point the motors at the beach in advance. The trade-off was performance. At 4 knots maximum speed were slower than almost any other watercraft in the invasion fleet. Their handling characteristics were poor. Essentially, you pointed them in a direction and hoped the motors and rudimentary steering could maintain course. In rough seas, they were nearly unmanageable without tug assistance, but this sacrifice bought something invaluable: numbers. By June 1944, dozens of Rhino ferries had been assembled in Britain. Hundreds more could be built quickly if needed because the manufacturing infrastructure already existed. The Pittsburgh Steel Corporation and other contractors could fabricate pontoons faster than shipyards could build specialized landing craft. The fastening system embodied the same philosophy, had tested multiple connection methods before settling on the stringer and wedge pin system. More sophisticated fasteners existed, threaded bolts, welded connections, hydraulic couplings, but all of these required either tools, time, or skills that might not be available on a contested beach. The wedge pin system could be operated with a hammer. The steel stringers essentially reinforced angle iron, distributed stress along the joint rather than concentrating it at fastening points. If a connection failed, it could be quickly repaired. If pontoons needed to be reconfigured into a different assembly, the pins could be knocked out and the structure reconfigured without cutting torch or welding equipment. Captain himself, speaking to engineers in 1944, explained his design philosophy. We cannot predict what conditions will exist at each landing site. We cannot know what equipment will be needed at each base. What we can do is provide a universal tool that competent men can adapt to whatever the situation demands. Pontoon is not the optimal solution for any single problem. It is an adequate solution for almost every problem. This philosophy extended to manufacturing and logistics. Pontoons were designed to nest for transport. Empty boxes stack efficiently. They could be shipped knocked down with panels and structural members flat packed to maximize cargo space efficiency. Alternatively, they could be shipped partially assembled on the decks of LSDs or strapped to the sides of cargo vessels. The contrast with British engineering approaches was notable. British military equipment often prioritized technical sophistication and specialized capability. American equipment increasingly prioritized mass production and operational simplicity. Neither approach was inherently superior, but for a global war requiring equipment in unprecedented quantities, the American philosophy of good enough quickly vast numbers proved decisive. The Rhino represented this philosophy. Perfected, it was slow, cumbersome, and unsophisticated. It was also available in sufficient quantities, operational in conditions that defeated purpose-built craft, and Simple enough that hastily trained crews could operate it effectively, these characteristics dismissed as weaknesses. By some observers, turned out to be precisely what Operation Overlord required, the Rhino fares operational. Record in the weeks and months following D-Day provides comprehensive data on how design philosophy translated into combat effectiveness. Between June 6 and October 1944, operating at Normandy transported 91,495 vehicles and 422,195 personnel. These numbers represent not merely logistical statistics, but the difference between a successful lodgment and potential disaster. The early days told the most dramatic story. On D+1 June 7, weather conditions deteriorated, seas became rougher, but Rhino ferries continued operating because their shallow draft allowed them to approach the beach in conditions that would have broached conventional landing craft. Then came the storm. On June 19, a violent gale struck the Normandy coast lasting 3 days. Winds exceeded 40, waves topped 6 feet. The American harbor, one of the two massive artificial harbors towed across the channel, was destroyed. The British was damaged but remained marginally operational. The storm reduced landing throughput by 60%. Over 800 vessels of various types were driven ashore or damaged. The carefully constructed logistics plan appeared to be in ruins. Recovery began on June 23. An army of 1,500 soldiers was dispatched to clear Omaha Beach of wrecked landing craft and debris. Every available vessel was pulled into the effort to resume discharge operations. The surprise came in the discharge statistics. Once operations resumed, both American beaches surpassed their previous rates. Utah moved 6,400 tons per day. Omaha reached 10,000 tons per day. The Rhino ferries, which planners had worried might be too fragile for sustained operations, were proving remarkably resilient. This resilience stemmed directly from the modular design. When a Rhino took damage, it didn't become a total loss. Individual pontoons could be replaced, motors could be swapped, the barge could be reconfigured if necessary. Maintenance crews working on the beaches developed impromptu repair techniques, welding patches onto punctured pontoons, substituting damaged sections with new units. CB pontoon operating units. The specialized construction battalion personnel trained in pontoon operations worked around the clock. These were not glamorous assignments. Crewing a Rhino meant 12-hour shifts piloting a slow, unwieldy barge through contested waters, approaching beaches still under occasional German artillery fire, coordinating with LSD crews and beach masters to synchronize loading and discharge operations. Petty Officer Robert Mitchell, 81st Naval Construction Battalion, described the work in a letter home in July 1944. We make 6 runs per shift if conditions are good, 4 if the weather is bad. Each run takes about 2 hours, 40 minutes. Out to the ships, 20 minutes loading, 40 minutes back to the beach, 20 minutes unloading. The ferry handles like a pregnant whale. The motors scream, but we barely make headway against the chop. Spray comes over the bow constantly. The vehicles sometimes shift if we hit waves. Wrong, but we get the job done. Last week we delivered 18 tanks, 40 trucks, and enough ammunition to supply a regiment. Nobody writes home about us, but the boys who use that ammunition appreciate our work. The tactical flexibility of the Rhino ferry system became apparent as operations evolved. Initially designed for shore cargo transfer, the ferries found new applications. When damaged LSDs needed emergency repairs but couldn't beach, normally Rhinos fied repair crews and equipment to the vessels. When casualties needed evacuation, Rhinos could be converted to ambulance ferries carrying wounded from beach aid stations to hospital ships offshore. When ammunition supply became critical for units pushing inland, Rhinos could be loaded with specific ordnance types and delivered directly to designated beach sectors. The system's adaptability proved its fundamental thesis. A simple, versatile platform could be adapted to whatever the situation required. By late June, with finally captured on D+24, logistics planners assessed the campaign's supply requirements. Port of Despite Liberation remained heavily damaged by German demolitions. The harbor entrance was blocked with sunken vessels. Cranes were destroyed. The electrical and heating plants were demolished. It would be weeks before could handle significant cargo. This meant the beaches would remain the primary logistics channel far longer than originally planned. The Rhino ferries, which were supposed to serve as stop gaps until proper port facilities became available, would remain essential through the summer of 1944. The human Cost of operations was relatively light by wartime standards, but not negligible. Several Rhino ferries were hit by German artillery fire with crew casualties. Some ferries were swamped in heavy seas. Engine failures occasionally left crews stranded, yet compared to the catastrophic losses suffered by landing craft in the initial assault waves, the Rhino crews got off relatively lightly. The comparison with other D-Day logistic solutions highlighted the Rhino fair's value proposition. The massive harbors had cost enormous resources to design, construct, and deploy. Thousands of workers had labored for months building the concrete, steel roadways, and other components. When the storm destroyed the American, that investment was lost. The Rhino ferries built from simple steel pontoons could be replaced quickly, damaged units could be repaired. New ferries could be assembled from stockpiled components within days. This meant that losses didn't compromise the system's effectiveness. By August 1944, with Allied forces breaking out from the Normandy bridgehead, over 850,000 men, 148,000 vehicles, and 570,000 tons of supplies had crossed the beaches. The Rhino ferries had been the horses of this vast logistics operation, delivering a substantial percentage of the heavy equipment that gave Allied forces their offensive capability. Final accounting would show that Captain's simple steel boxes had decisively outperformed more sophisticated alternatives, not because they were technically superior, they weren't, but because they were available in sufficient numbers, operationally resilient, and adaptable to evolving tactical requirements. The complete story of naval pontoons and Rhino ferries reveals production and deployment statistics that demonstrate the system's strategic impact. Pontoon production during World War II reached industrial scale. The Pittsburgh Steel Corporation and other contractors manufactured thousands of pontoon units monthly. 5 pontoon assembly detachments, pads consisting of 17 officers and 418 enlisted men, each operated assembly lines that could produce approximately 1,800 steel pontoons per month per detachment. Remote locations. These pads worked generally 2 12-hour shifts each day to maintain production. The standard T6 pontoon, the rectangular 5TX57 unit, formed the basis of most assemblies. The T7 variant, measuring 5x7x7, provided additional buoyancy for specialized applications. Curved bow pontoons gave directional stability to barges and ferries. For the Normandy invasion specifically, approximately 55 Rhino ferries were prepared before D-Day. Distribution allocated 31 ferries to American beaches, Utah and Omaha, and 41 to British and Canadian beaches, Gold, Juneau, and Sword. Additional components were stockpiled for rapid assembly of replacement ferries. The operational statistics from Normandy quantify the system's effectiveness. From June through October 1944, Rhino ferries transport 91,495 vehicles and 422,195 personnel. In the critical first 10 days, approximately 85% of all vehicular equipment landed on Utah and Omaha beaches arrived via Rhino ferry. Comparison with purpose-built landing craft reveals instructive contrasts. LSD's landing ship tank displacement approximately 4,000 tons. Cargo capacity roughly 100 troops plus 16 to 19 tons of equipment. Draft wind beat 8 to 14, speed 10 knots, required specialized shipyard construction with skilled naval architects, welders, and ship fitters. Construction time approximately 6 to 8 months per vessel. Total built during war approximately 150 vessels. Rhino ferries displacement approximately 275 tons. Cargo capacity 275 tons. When Rhino ferries were damaged, replacement pontoons could be welded in place within days, often by CB repair crews working directly on the beach. New ferries could be assembled from stockpiled components within a week. A damaged Rhino didn't require a shipyard, it required a welding torch and spare pontoons. The pontoon system found applications throughout the war in multiple theaters. In the Pacific, pontoon causeways and FIs operated at Atu Canal, the Philippines, and numerous other islands. The ability to establish logistics infrastructure rapidly on undeveloped shores proved decisive in campaigns where every day of delay allowed Japanese defenders to strengthen positions. The broader lesson from the pontoon story involves design philosophy and operational requirements. Military equipment designers face constant tension between optimization and versatility. Purpose-built solutions perform better at specific tasks, multi-purpose solutions handle a broader range of challenges, captains. Genius lay in recognizing that World War II's scale and scope favored versatility. Over specialization, the war would be fought across every continent in every climate under every imaginable condition. What American forces needed wasn't the single best solution for each specific problem that would require thousands of different specialized tools. What they needed was a single, adequate solution for a wide range of problems. The naval pontoon provided exactly this. It wasn't the best floating platform design, it wasn't the fastest barge, it wasn't the most sophisticated engineering solution, but it was good enough for most situations, simple enough to be mass and versatile enough to be reconfigured for whatever purpose the tactical situation demanded. Survivor testimony underscores the system's human impact. Staff Sergeant James Wilson, who watched Rhino ferries deliver tanks to Omaha Beach on D+1, recalled decades later, those ferries looked like something a desperate engineer cobbled together in an afternoon, just boxes bolted together. But they kept coming through the smoke and the spray, bringing us the armor we desperately needed. CB Chief Petty Officer Thomas Henderson, who operated Rhino Ferry RHF-18 throughout the Normandy campaign, reflected in a 1985 interview, "We weren't heroes, we didn't charge enemy positions, we just drove our clumsy barge back and forth, loading vehicles, delivering them to the beach, going back for more 12-hour shifts day after day. But when I see the statistics, 91,000 vehicles delivered, 420,000 personnel transported, I realize we were part of something significant." The final irony is that the Rhino Ferry, for all its impact on D-Day, remains largely unknown outside military history circles. The massive Mulberry harbors captured public imagination and became symbols of Allied ingenuity, but it was the unglamorous Rhino Ferry assembled from simple steel boxes that actually delivered the critical tonnage in the invasion's pivotal early days. April 15, 1944, England. Lieutenant Commander Harold Parker stands at the dock's edge watching CBS assemble another Rhino. 52 days until D-Day, September 2, 1943, Washington, D.C. White House guest bedroom. In the evening hours, Captain John Locke finds himself demonstrating his folding barge model on Churchill's bed covers. The Prime Minister, propped up in bed, heaps praise on the novel landing pontoon that had been of such benefit. The Sicilian invasion, the examination that began with skepticism. Lieutenant Commander Parker, questioning whether simple steel boxes could solve complex military logistics problems, concluded with vindication. The naval pontoon and its offspring, the Rhino, weren't poorly designed, they were brilliantly designed to achieve specific goals: mass production, operational versatility, tactical resilience, and strategic availability. Those goals simply did not include aesthetic elegance, technical sophistication, or performance optimization, and in that single fact lies the entire story of why amphibious operations succeeded at a scale unprecedented in military history. The physical evidence remains sparse today. Rusted Rhino Ferry pontoons lie exposed at low tide on Utah Beach near sand, corroded remnants of steel boxes that helped change the world. The U.S. Navy CB Museum in Port California maintains historical exhibits documenting the pontoon's construction and deployment, but no intact Rhino Ferry survives, preserved for posterity. Perhaps this is fitting. The pontoons were never meant to be monuments. They were meant to be tools used hard, maintained minimally, replaced when damaged, reconfigured as situations changed. Their disposability was a design feature, not a flaw. The lesson captain's work teaches transcends specific equipment or tactics. It speaks to fundamental questions about how complex problems get solved under crisis conditions. Sophisticated solutions often fail not because they're poorly conceived, but because they're fragile. They depend on specialized expertise, perfect conditions, or elaborate support infrastructure. When any component fails, the entire system collapses. Simple solutions succeed not because they're optimal, but because they're robust. They accommodate imperfect conditions, non-expert operators, and inevitable failures. Individual components can fail without system collapse. Damage can be repaired quickly. Replacements can be manufactured rapidly. World War II fought across all oceans and continents simultaneously, required robust solutions more than optimal ones. American military production philosophy, good enough, quickly, in overwhelming numbers, proved decisively superior to approaches prioritizing technical excellence in limited quantities. The naval Pontoon embodied this philosophy perfectly. Each steel box represented compromise, heavier than airfield pontoons, simpler than purpose-built landing craft, slower than conventional barges, but each box could be mass, easily transported, rapidly assembled, and continuously adapted to changing tactical requirements. When Lieutenant Commander Parker watched CBS bolt together another Rhino ferry in Falmouth on April 15, 1944, he understood something that wouldn't be proven until June 6. This collection of steel boxes would deliver more tanks to beaches in the first critical days than all the sophisticated landing craft purpose-designed for exactly that mission, because sometimes the war isn't won by the best solution. It's won by the solution that's actually available when and where it's needed in sufficient quantities, operated by whoever happens to be present under whatever conditions happen to prevail. Captain Lake's cigar box model assembled with kite sticks in a Washington office in 1940 captured this truth before the war even began. The boxes floating in Falmouth Harbor in 1944 proved it under fire. The rusted pontoons exposed at low tide on Utah Beach today stand as silent testimony to a fundamental principle of military logistics: simple, versatile, robust, and available beats sophisticated, specialized, optimized, and scarce every single time. The floating Lego bricks that won D-Day weren't the technology anyone would have chosen if starting from scratch. They were the technology that actually worked when nothing else could. And in June 1944, on beaches where the fate of Western civilization hung in the balance, that made all the